Hello, everyone. Come on in. Anybody have any questions while we're waiting for everybody else to get in? No. Can someone speak so I can see if your speakers are working for me?
Hello. Yeah.
Thank you, Victoria. And Abby, I think.
Yes, I did have a question. My Zoom's being really weird today.
Yeah.
I was hoping you could reiterate from last week which chapters are and aren't on the final. It's 43 and 44, correct?
That's correct, yes.
Okay, but
So
and then as far as
include
my
36.
mastering homework.
Yes,
Okay.
I was saying it will include chapter 36, but I haven't decided yet. 44 is supposed to be regular homework. I might make it extra credit, but I still didn't create the conceptual homework for 44. But like I said, even if I do that, that's definitely going to be extra credit.
Okay, and then on our homeworks as well, you're dropping the 2 lowest homeworks and any conceptuals?
I think I'd said in my syllabus that I was going to drop either no conceptuals or 1 conceptual and 2 of the other ones homeworks, that is. As far as I know, the names on the test where it says the chapters in them, someone just asked this, Jared did. As far as I know, those names are accurate, those chapters are accurate, and the final should be as well. So our final will really be on basically 1 through 11 plus chapter 36. I decided not to put 43 and 44 on the final. I just gave you that extra test that you have to take, and that'll cover enough of what you need to know for 43 and 44. Anything else? My wife just got home and I smell this wonderful smell. I was like, man, my wife smells so good. And evidently it's a hand sanitizer. She always smells good too, though, of course. All right, everybody. Well, I guess I'll go ahead and get started. I've gotten some stuff written down on the top of the page, just reminders like the speed of light. And if you pull down your notes, if you did it right after class, then you might need to go back and do it again. But your notes from Monday, I posted them and then I went back and posted them again because I wanted you to have the names of all the people that I mentioned. So what I did was I listed all the names and a couple of other ones that I didn't mention or whose names I'd actually forgot. And I put them all in there and I put it on the second page of the notes for last class. So if you download the notes for that last class from my Google Docs page, you'll get the names of all these characters that I'm saying, more or less in order. So I would definitely recommend doing that. When we last spoke, we had talked about how, in fact, the evidence of the Big Bang came to us experimentally. I mean, we had some evidence from the general theory of relativity. Alexander Friedman in Russia had worked out general relativity on a cosmological scale and found that it was telling us the universe was expanding. But he was in the backwaters of Russia that was going through a lot of crap in the 15s through 1925s or so. So a lot of people didn't see his stuff. However, Georges Lemaitre, and I don't know if you're supposed to pronounce that George or not, because I'm not a foreign dude and I've never had much experience outside the country, so I'm kind of a loser that way. But anyways, Georges Lemaitre was a Belgian priest. And he, in fact, had also done the same calculation, not knowing anything that Alexander Friedman had done it, and found that general relativity was telling us, hey, the universe used to be really, 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 really small. And in fact, it spread from a pinpoint infinitely small object to as big as we see it now. And he's in his calculations, we are getting notifications that your connection is unstable. Well, that sucks. Am I stopping and dragging a lot?
You were before, but it just stopped. It just cleared up.
Okay,
I'm no longer getting that notification.
Hopefully that's done. Let me see. I don't see any other apps running. Oh, let's see here. I think it could be this. So what I was saying was that Lemaitre, again, a Belgian priest, had calculated that Einstein's general theory of relativity was predicting the expansion of the universe, and he sent it to Einstein. And then Einstein wrote back to him and said, your math is correct, but your physics is abominable, because Einstein believed in a static universe. And a static universe, meaning one that's never changed and never will change. It will always look exactly the same, at least on a big scale. So he didn't believe in an expanding or contracting universe, or even a changing universe. He was like the guy Fred Hoyle, whose name I didn't put on there, because if you watch the Universe season 1, the season finale, it's called Beyond the Big Bang. That's very excellent. I highly recommend you watch it to get a history of this stuff. And it's really an excellent production. It's maybe an hour and 45 minutes, and it goes through all of the stuff I've been talking about. But anyways, Fred Hoyle and Einstein both believed in the static state of the universe. So he was just telling Lemaitre that, your physics is wrong. And what he meant by physics is his understanding of, as he's many times before said, God's universe and how God created it. And he did not think God would have created a universe that was not static. Again, he's getting a little big for his britches in that case, because it ultimately turned out he was wrong. And he said, his cosmological constant, which is his capital lambda, it looks like this, basically, that's a capital lambda. He put that in his equation to make the universe not expanding, specifically because there was no evidence that it did expand. And he called it the greatest blunder of his life. And later he said God was punishing me because he had given so much trouble to so-called experts that he made him an expert with a big mistake on his back too. So that was a really big deal. But the amazing part is the general theory of relativity is still predicting to this day, like September 5th, September 19th, I think it was, 2019, I think it was. So maybe it was September 5th, 2019. We finally got the first evidence that's direct evidence of a black hole, which Einstein's theory predicted. We got the first evidence of gravitational radiation, which was evidence that Einstein's theory predicted. And then we got evidence that basically gravity waves exist. I don't know what I said from my last one. I blanked out for a second there, but anyways, we got direct evidence of a black hole. We got direct evidence of gravity waves, which Einstein's theory predicted. And we had worked out, before the instruments came online, worked out what we would see if two black holes collided into each other, and used Einstein's equations to predict exactly what the gravitational wave signature would be. And lo and behold, that was a prediction of Einstein's general theory of relativity that we confirmed on that same day. So it's pretty amazing that it's still doing that, and that it did it so early as well, that it predicted the expansion of the universe. So that's where we sort of were. We hadn't really talked too much about beyond that, but I did tell you that Hubble was looking at nebulas. I think I even listed that nebula is, I think, Latin. It could be Greek, but I'm pretty sure it was Latin for cloud. And it just sort of meant like a cloudy spot. It could be some confusion, that sort of thing. So you often hear people say, well, that's a nebulous concept. And they're just meaning it's not very clear to see, or it's not very clear to understand. So the nebula originally were just things that you saw in the night sky that looked kind of furry or blurry or something like that. And that literally means sort of furry too. You would look at them with the naked eye, and it just looks like you can, sometimes you can only see it out the side of your eye a little bit, but it didn't look like individual stars. So they named them nebulas. And after we got telescopes, really big telescopes, like the 100-inch on the top of the mountain in Los Angeles where Hubble was working, it became obvious that one of those, the Andromeda Nebula, which is in the constellation Andromeda, was in fact another island of stars like the one we were in. And we didn't know that was what we were in before. We had this sort of gristmill looking shape that astronomers had worked out, and they might have thought the most distant stars maybe extended maybe 10,000 light years out from the center. And I don't know exactly what that figure is. I'm just saying roughly something small compared to the distance to this galaxy. So I've actually set it a couple different values in these videos I've been doing for this week. The main thing is I wanted you to understand that their sort of picture of how far they could reach out from us and find stars was really small compared to the distance that Hubble found was how far away Andromeda was. So when he looked at it, he said, this is actually an island of stars. He could see individual stars, and he realized it was a what we would call now a galaxy. So that's one of the things that nebulas can become, is they turned out to be galaxies. Another thing they turn out to become is actually a cloud. That's a incubator for stars. In fact, you'll look at the Great Orion Nebula is one of them. And when you look at that, you'll see even with a binoculars, you can see some little clouds and colors and stuff like that. And you see some little bright stars. And what that is the birthplace of stars. Stars are being born there. And you're seeing clouds of gas and dust that are required to make a star. So those nebulas became nebulas. The nebulas that were galaxies became galaxies. And then the other nebulas turned out to be star clusters. And there's open clusters and closed clusters and all this good stuff. But really the main thing is they're buttloads of stars in a small area. Okay. Like if you look right in between the end of Gemini and the head of Leo the lion, which looks like a backwards question mark or a sickle, you'll see a little double triangle. So it's like triangle and then another triangle inside of that. And you'll see something sort of blurry in the middle. That's the constellation Cancer. And that blurry thing is a collection of millions of stars, or at least hundreds of thousands of stars. And you can see that with binoculars as well. So that's what the nebulas turned out to be. But when Hubble looked at this, he realized, okay, we've got a galaxy here. That's something neat. That's something new. But he was also able to use Henrietta Swan's Leavitt's data and discovery, where she had basically put together that the mechanism of a star, a certain type of star, would require that star to put out a certain amount of luminosity. In other words, a certain amount of energy per second. And that amount of energy put out per second would go like this. Okay. And in fact, the amount of energy it put out per second was directly related in some way mathematically. I don't mean directly like multiplicative, but was related mathematically in some way to how long it took for it to go from a peak to a peak again. And the data she had wasn't that great, but she was exactly right about the whole process. So Hubble was able to use that information to see how far Andromeda was away. And in fact, it was on the order he thought of maybe hundreds of thousands of light years away. It actually turns out to be 2.5 million light years away, which is a really big deal. But still, the main point was it was way farther than the reaches of what we thought was our universe before that. So that was a really big deal. And that's how I concluded that there were, in fact, several galaxies, and we were just but one of them. So I'm looking over here. I'm trying to see it. It just told me again that my resources are okay. So I'm going to close one of the windows I have working in the background, which is my YouTube channel. I just posted 2 new videos up there. So I'm going to close that, and I'm going to close my other channel here. Okay, so that's all good. All right, so hopefully that'll take away some of the resources being used. So Hubble saw that, but then he saw something even deeper. Okay, so he was able to put that back there, and what he found out was that galaxies were all moving, and he could tell that from something called the Doppler shift. So for instance, if a color's red, just like if a sound has a 250 hertz signal, but the car putting out that sound drives towards you, it'll go from 250 hertz to something like 260 hertz, and it'll be more high pitch. It'll go wow, wow, instead of wow, wow, right? So that wee woo guy, right? That A1 number one, that's A number one. You know, I'm going on with a TikTok there. So anyways, that is the Doppler effect. And in fact, when the car goes past you, it'll go from wow, 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 like that, where it really gets deeper. And that's because now the waves are being stretched out behind it. That's in sound, and we've been using that, and y'all probably known that for some time about sound. But when you start to approach, you know, really high speeds, or if you can detect speeds really precisely, then you can see that the color of light does so as well. So if a star is red and it's coming towards you, then it will actually be blue shifted. In other words, its wavelength is shorter. So it goes from this wavelength when it's coming towards you to this wavelength. So it's this wavelength when it's sitting still, but when it comes towards you, it shrinks. It's almost like it's pushing these little springs out, but then it runs towards it. So the front of the spring gets closer to the next front of the spring. That's the Doppler effect. If it's actually going away from you, it's called red shifted. And that's because red is the long end of the visible spectrum. But what he discovered was that essentially all galaxies are red shifted. And from that red shift, he could detect how fast they were going. And here's the weird part. He discovered that when a galaxy, say, is 100, now I'm going to use another unit of distance here called the megaparsec. The main thing is to know that, megaparsec's a unit of distance. It's 1,000,000 parsecs, and a parsec is about 3.26 light years, which we'll discuss in a second. So it's a really big distance, right? So if he sees a galaxy at 100 megaparsecs, say moving at 50 meters per second, then if he finds another galaxy that is instead at 200 megaparsecs, that's twice as far away, then that galaxy was actually moving at 100 meters per second. And if he found one 4 times as far away, so 200 megaparsecs away, then he'd find it moving at 200 meters per second. So that's amazing. And he found it everywhere. And not only that, he found it that if you happen to be one of those other galaxies, you'd measure the exact same thing with respect to the galaxies that you would be looking at from there. And there's only one way we can interpret that. When you have that kind of relationship between velocity and distance, it's clear that the object isn't actually moving through space that fast, because in principle, if you go far enough away, it will be going infinitely fast, which exceeds the speed of light, right? That's one reason you can think about that. But in fact, another reason is that the only way that works is if the space itself is getting bigger. So the distance between them is getting bigger. The best example I can give you of that is, imagine blowing up a balloon to say this big. And then you go 1 centimeter down from the top and you draw a continuous circle around it. And then you go another centimeter down and draw a continuous circle, and another centimeter, another, all that till it's completely covered in circles. Now you take dead center in the middle of the top circle and you draw a dot, and that represents a galaxy. And then you go over 1 centimeter and draw another dot, 2 centimeters, go another dot, 3 centimeters, go another dot, all around that same line, and then step down and right below that first one, put another one and do 1 centimeter all the way around and keep doing that. Okay. Now all of your nearest neighbors are really 1 centimeter away. Now what I want you to do is you take that balloon that was this big and you blow it up. Now it's like this big, and now you measure the distance between that first dot and the second dot on any line. It's now like 2 centimeters away. Well, guess what? Now the one that was 2 centimeters away is in fact 4 centimeters away. So it's like it actually traveled twice as fast. It traveled 2 centimeters in the time that it took the other one to travel 1 centimeter, because that's the same period of time from when we had it this size and then until we blew it up to that bigger size. And if you go a third away, that would actually be 6 centimeters away. And of course, that's 6 compared to 1. So since it was 3 times as far, it obviously went 3 times as fast. So that's how that works. And that's the only way we could picture it. So what Hubble found was, in fact, this. Turn on my document cam. He found, in fact, that the velocities in, say, meters per second or kilometers per second or whatever versus megaparsecs, that's how far they are away from each other. And by the way, 1 parsec is equal to 3.26 light years. And what he found was, when he plotted those galaxies, they made a straight line. They weren't the prettiest of straight lines, but they were, very typical for some early data, right? And he found out that the slope of this line, or eventually we worked out that the slope of this line is what we call the Hubble constant, which is H0. And that is, in fact, 71 kilometers per second per megaparsec. So if you're 1 megaparsec away, obviously Hubble's law says you should be moving at 71 kilometers per second away from us. If you're 2 megaparsecs away, you can see that's 14.2. If you're 3, you're 21.3, so on and so forth. And that's what this is called Hubble's law. And in principle, that's one of the ways we can use to measure distance. In fact, that's the hardest thing you can do in astronomy, astrophysics, and cosmology is measuring distance. So we've got to find ways of doing that. So this is what Hubble found. Now, in the meantime, and well before this, in fact, as I told you, Alexander Friedman and Georges Lemaitre had suggested that the universe used to be a lot smaller, and in fact that all the galaxies were at one time right next to each other, which is exactly what Hubble's law is saying too, only that was on the order of 3 or 4 years later, right? Because if they're spreading apart, then obviously some time ago they were actually all together. And if you take this number and flip it over and then convert it, you'll get approximately 13, I think it's 13.3 billion years. So that is what Hubble's, the inverse or the reciprocal of Hubble's constant is. It gives you the age of the universe. Okay. So it predicted the very beginning of the universe. And again, that assumes that the universe always ran at the same rate. We've since discovered that, oh, poop, the universe is actually expanding and the expansion rate is increasing. That's why we came up with the dark energy scenario. So that's a bit of a problem. But either way, we're still pretty confident the universe is about 13 billion years old. But as I said, Lemaitre and Friedman had already predicted this, as did Einstein's general theory of relativity. And in fact, there was this professor, George Gamow. Now, he had a really bright theoretical mathematical grad student named Ralph Alpher. And in fact, let me share a screen with you for a second. In fact, that's Ralph Alpher right there. That's George Gamow. And this guy is Robert Herman. He was another grad student, not quite the caliber of Ralph Alpher, but he did contribute to this calculation. And Gamow was their PhD advisor. And this is a great book, by the way. I've read it several times. And he even puts in the appendix the calculations that he did. So Ralph Alpher actually puts the calculations that he did for detecting some of the stuff I'm getting ready to tell you about. So that's Ralph Alpher. And like I said, Robert Herman, which is a little bit lesser known, but I'm glad to let him be known at all because they really got screwed over. Okay. So George Gamow had learned about the predictions of Lemaitre, had learned about the predictions of the general theory of relativity, and in fact believed it. And George Gamow was a really brilliant physicist, a brilliant idea guy, but he wasn't that strong at mathematical physics and that sort of thing. So he asked his grad student to make some predictions based on the idea that Lemaitre was coming off, had given. And what he found was, in fact, if you take the amount of hydrogen and helium in the universe, so this is given, he could predict exactly what would come out of the Big Bang. And in fact, he predicted hydrogen, helium, carbon, or excuse me, not carbon, hydrogen, helium, lithium, and beryllium and boron, hydrogen, helium, lithium, beryllium, and boron. And using the percentages of this, so given amount, so given that the amount of hydrogen and helium in the universe, he was able to predict how much lithium and beryllium should be in the universe naturally as well. And guess what? He's right. And in fact, we continue to do that to this day, and we continue to get that the Big Bang predicts the right amount of helium, hydrogen, helium, lithium, beryllium, and boron, as well as other elements, because we're going to learn that there's another process going on here. So he predicted that. He predicted, in fact, that this would all be made within the first 6 minutes. He predicted, in fact, the rate of expansion. How fast the universe would be growing. And he predicted that there would be a microwave and normally we start that with cosmic, so I'll stick cosmic in there. Cosmic microwave background radiation. Okay, what this was about now is crazy, but basically as something gets bigger and bigger and bigger, it cools down. That's what some of the ideal gas law, and a lot of this is actually done with the ideal gas law, believe it or not. That and just understanding basic nuclear physics and trying to tell what are likely collisions at what temperatures, right? So what he computed was that around 3000 Kelvin, once the universe reached that temperature, which is literally the universe is all the matter, all the energy, all the dark matter, all the dark energy, and all the space within it. Once it got to a certain size, its temperature would reach 3000 Kelvin. At 3000 Kelvin, the baryons can come together with the leptons. specifically the neutrons and protons can come together to make nuclei, and the electrons can hover around that, and that's when this stuff is done. But when they start grouping together like that at 3000 Kelvin, they can actually stay. So the energy that the individual particles that have been created from the Big Bang, those energies are very discrete. In other words, there's only certain ones that these collections of particles can accept. Whereas before that, since they were free particles, they could accept any energy level whatsoever. It's sort of like from the Bohr model of the atom, which remember we had a nucleus, and then you had a orbit for a electron, and then another orbit for electron. And with that was associated a very specific energy, E1, and this one E2, and this one E3. And what Bohr was showing with this, and that's why that Bohr model was important, is that the only energy this atom can accept is E2 minus E1. That would cause the electron to jump up from here to here. Or E2 or E3 minus E1, that would make this electron jump up to there. Or E3 minus E2, because that would make the electron jump up to there. So if that was the only three orbitals that particular atom had, then that's the only energy it could accept. And then quantum mechanics told us that energy is equal to HF, or since c, the speed of light, is equal to frequency times wavelength, you can say hc over lambda. So you can either associate this energy going from here to here with a frequency or a wavelength, or just a color, right? That would be acceptable if it happens to be in the visible spectrum. So before these particles are grouped together in such a way like this, they can absorb any energy, all the energies between 0 and E1, and in between E1 and E2 and E2 and E3. But at 3000 Kelvin, acceptable absorbable energy is quantized. So again, it means only certain wavelengths can come out. Well, guess what? Before that, every bit of light was being absorbed by all the particles. So after that, an immense amount of light is shining from everywhere. And the universe might have been something like this at 3000 Kelvin, and it would be black. And then when it got, let's say, 3001 Kelvin, it was light and it gotten a little bigger. And in fact, since that time, which by the way, this time's around 380,000 years after the Big Bang. So the universe was dark and black and very small, and it got bigger little bit by little bit. And if you look on page 1216, you'll see a plot of how quickly it grew and various time periods during that. But once it gets to 380,000 years, it's 3000 Kelvin. And at that point, you can start taking and seeing energy sent out as light, because before that, everything was captured by all the free particles. After that, everything except very specific wavelengths was captured. So all that light went out in all directions in the universe. So he expected that people could see a cosmic microwave background radiation coming from every direction in space, and he predicted it would be around 3.0 Kelvin. Okay, what do we mean by that? Well, what we mean is if you made a plot, and you've seen these plots before, of course, of intensity versus wavelength, you would get a very steep line like this, would come over and reach a peak, and then it would gradually fall down. That wavelength, called lambda peak, is given by Wien's law to say that lambda peak is equal to 2.30 or something like that, times 10 to the third meters Kelvin over temperature. So when you put in 3 Kelvin there, you get out the wavelength of the radiation. And he calculated that wavelength by realizing how big the universe was at this point and how big it was on the day he made the calculation. So by using the rate of expansion, he would know that the wavelength would go from this size, which is say X, and then let's say the universe went from this, let's say this is X, and I'll call this a capital X just to differentiate it from that. And then this is, let's say, Y, and then let's say now the universe is this big and it's Z big. Okay, that means the whole entire observable universe all the way across that, that's how big it is. Well, what he's saying now is that this distance of this radiation that's coming towards you from here to here, instead of it being X, it's now going to be X times Z over X. In other words, however much the universe tripled in size, quadrupled in size, whatever it did, if it 84 billion and tupled in size, then this number right here will be 84 billion. And that's how he got the wavelength. Guess what? When they finally found this radiation, and immediately the people at UC Berkeley were looking for it, they had built a little microwave antenna called the Dickey radiometer. And that's at UC Berkeley. And they were looking for it, couldn't find it. Turns out their antenna wasn't big enough. But in New Jersey, there was a guy by the name of Bob Wilson and another guy by the name of Arno Penzias. And they worked for Bell Labs. In New Jersey. And they had a huge antenna that looked like this. And I'm talking huge, like this thing's 20, 30, 40 feet long or something like that, right? And it had a little house built on it. And they were actually doing what was the legwork that needed to be done for us to have cell phones and satellite communications and stuff like that. And actually it was a double one, so they had some other over here or something. But they kept getting this stupid pesky noise in their signals. So they like swept out the insides and tried to treat it like maybe it was, you know, bird droppings in there. They looked for local airports or military bases sending out signals that were screwing it up. And none of that came to fruition. In fact, nothing happened until all of a sudden they were reading one of the journals for physics, and they found that they were looking for this background radiation that should be omnidirectional, coming from every which way, and roughly what it was. And they're like, holy crap, I think we got that. So they write up a paper, show they have it, and they found it was at T equals 2.7 Kelvin. So he was off by 0.3 out of 3. So that's not bad for someone predicting it, you know, from a calculation as a grad student. So guess what? These guys won the Nobel Prize. And they hadn't even heard of Ralph Alpher and Robert Herman. They of course knew of George Gamow. Everybody knew of George Gamow. He wrote popular books to explain physics to people, and you can find a lot of those still around today. I have like all of them. But anyways, they were completely ignored, and here's the reason. Notice Ralph Alpher sounds like alpha, and George Gamow sounds like gamma. Well, George Gamow was a bit of a huckster, jokester, if you will, within the physics community, and everybody loved him because he was hilarious, but he was also brilliant, so they liked him for that as well. But he just could not imagine a scenario in which they'd publish a paper with alpha and gamma and not put a beta in there. So he called his friend Hans Bethe, who also later won a Nobel Prize, by the way, so it's worthwhile to know this kick butt dude. He was a German immigrant, and in fact his somewhat instrumental in us being able to get a nuclear weapon. He was part of the Manhattan Project. But Hans Bethe, who a lot of people call Beta because he was literally like the second best at everything. So he's really a brilliant, brilliant man. But anyways, he's talked him into, or tried to talk him into putting his name on this paper, because he said everybody will call it the alpha, beta, gamma paper. So the alpha, beta, gamma paper. Well, eventually, Hans Bethe said, well, okay, I'll do it since the grad students don't seem upset about it or anything like that. Well, guess what? The problem was they published it. Everybody saw immediately that it was alpha, Bethe, and gamma, and they knew gamma being in it. It was just a joke. So they never even read it. It was really a horrible happenstance. And poor Ralph Alpher literally just died like in the last 2 to 5 years, or 2 to 10 years maybe. He was at Union College. Anybody know anything special about Union College? It might be Union University now. Barbara Streisand went there. That's sort of the major fan. It's actually a very nice quality university or college or whatever you want to call it. But Ralph Alpher was a professor there until he died. But anyway, he went to Union College, and never, ever, ever did he get the recognition that he deserved. I mean, the people that discovered what he predicted. Now, he predicted it. You know, this is a dude that predicted it, and he got nothing for it. That's really horrible. But of course, Bob Wilson and Arno Penzias did, in fact, win the Nobel Prize for it. So that was where we got into the scenario of a Big Bang. Now, what is the Big Bang? So here's the time where I need to show you my face, because I got to make a lot of goofy expressions and stuff like that. And I got to gesticulate, which isn't a bad word. It means moving your hands while you talk. Okay. Masticate isn't either. That means chewing. So there's a lot of neat words in the English language that sound something different. But anyways, so the Big Bang is a very special thing. Okay, the Big Bang, as best we can tell, created the universe. Okay, now in order for you to understand that, I feel like I got something in my eye. In order for you to understand that, you've got to understand what the universe is. I haven't talked about dark matter and not very much about dark energy, but basically, if you consider all the matter in between the center of the galaxy, say our galaxy, and where we are about 26,000 light years out from the center, our galaxy is about 100,000 light years across both ways, sort of. It's about 2,000 light years thick, but it's also got sort of an egg yolk, like you were boiling a cracked egg on the top of water, because it's lighter than water. It's going to sit on top, and then you have a bulb for the yolk in the middle, so it come down a little bit in the middle and up a little bit in the top. Well, the egg white is about 2,000 light years thick, 100,000 light years this way, and then the actual egg yolks maybe extend another 2,000 to 3,000 light years above and below that disk. That's what our galaxy is shaped like, but it's actually in little spirals. So it looks like a little bit like a hurricane. So there's a nucleus or a center of the galaxy, and then there's a spiral arm, and then there's another spiral arm, and 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 some of those might even have some spiral little arms off of them. But that's what our galaxy is. And I told you earlier that our galaxy actually goes around that 26,000 light year radius. It goes around our galaxy about once every 250 million years. That means it's moving about 200 meters per second. And in fact, if you use Newton's law of gravity for that, and you consider other objects in our universe or in our galaxy as well, and figure out how fast they should be going based on the amount of matter inside, you find out that the matter inside is always less than the matter you need to explain that velocity. So that's where dark energy or dark matter came in. They said there must be some invisible matter that's causing these planets to behave differently from what Newton and Einstein said. So you can do this with general relativity or with Newton's gravity. Either way, it only depends on the mass inside, and they consistently get a bigger mass inside than they can actually account for. So they had to come up with the idea of dark matter. Since then, we found locations where dark matter is, and we can see stuff moving around it, so we know it's a reality. It's a real thing. Now, I also mentioned that the Big Bang caused the universe to expand, and if there's enough mass, it would expand, 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 slow down, slow down, slow down, come to a stop. If there wasn't enough mass to do that, and by the way, if it's that much mass, it's going to come to a stop and then maybe even pull backwards, or it could just go forever and just come to a stop at infinitely long time. Or it could be less mass in which case it's going to continue expanding forever, even though it's slowing down. Well, guess what? The data came in and it turns out it's not slowing down, it's speeding up. And we think that's due to some hidden energy that we don't know of. So we call that dark energy. So that's what those things are. So when I say the universe, what the universe means is all the matter, all the energy, all the dark matter, all the dark energy. And by the way, the matter and energy that we know of is only about 2%. And then here's the big thing, and all the space itself. So the universe is the space itself. There was not this giant empty space. And people think this is what the Big Bang is. This is not what the Big Bang is. People think that there was this giant empty void. And from some location in that empty void, there was one little nothing, really. But out of that one little nothing exploded all the matter that made the Big Bang. That's not it, because if that was it, you could trace back the velocities of all the galaxies and which way they're moving, and they would all come together at one point in space, and we don't have any such point. Okay, as I told you, it would be more like the dots drawn on that balloon before and after we blew it up. And in that sense, on the balloon, you have no idea about there being an inside of the balloon or outside of the balloon. You just know the balloon surface, and that's what we're dealing with. That's what the universe is. So the universe really created, in the Big Bang, the universe was created, and it created a space and some matter, hydrogen, helium, lithium, and beryllium, and a buttload of energy, and it expanded. And Alan Guth, realizing there was a major problem, specifically the universe got big and got big fast, but somehow the universe, as big as it is, if you plot temperature in every direction around the universe, it turns out the highest temperature spot in the universe versus the lowest temperature spot in the universe, on a grand scale, mind you, differs by on the order of 8 decimal places. So it's a really minute difference in temperature from the hottest to the coldest. And you can't explain that. Heat can't flow that fast through space to make the whole thing equilibrate that well. So he hypothesized that there was a period called expansion very early on, like 10 to the negative 27 seconds early, where it expanded humongously. Maybe a factor of 1,000 or 1,000,000 or 10 million or something like that. And then from there on out, it just started expanding at a normal rate that we've since determined to be accelerating. So he came up with that idea. It's called inflation. It's not a really easy thing to test. I once heard a cosmologist say it's like trying to nail jelly to a wall. So he didn't give us a lot of details. He just gave us a hypothesis that was not easily canceled. So that's what the Big Bang is. And from Ralph Alpher's calculations, we're only going to get those elements. But over time, after we get through that 3,000 Kelvin part, not only can matter group together to make atoms, but atoms can group together to make clouds. We don't exactly know, but it seems like the dark matter may have played some role, maybe even the dark energy in that early universe that created sort of something like stars, but it might have also formed something like galaxies at the same time. And of course, you'd normally think the stars were there and then the stars came towards each other and that made galaxies. And then of course, galaxies can run into each other and they can make weirder galaxies. And you only have a few types of galaxies, but you can tell, well, a couple of them are obviously something that's been in a car wreck. So that's the universe as we see it. But all of that is now what we get out of the universe, but we still got this problem. The universe only created hydrogen, helium, lithium, beryllium, and boron. The periodic table's got like 120 things on it, right? So that's where nucleosynthesis comes in. And it turns out, in order for you to have the elements necessary for life, iron in our blood, that's a necessary element. That's not in the list of hydrogen, helium, lithium, beryllium, and boron, right? There's other elements too. We need, for instance, silver to make our wives' earrings and our gold to make my wife's watches and necklaces. And we need mercury and lead to make my fillings, maybe not lead, but mercury at least to make my fillings, all that kind of stuff. That stuff exists. We know it exists. But we also know stuff like, gold, platinum, silver, they're expensive. So they must be pretty rare. And in fact, they are, because it turns out that the way we got those elements beyond hydrogen, helium, lithium, and beryllium is the way a star lives. So if you take a star and it's 8 to any number of solar masses large, in other words, a big star. So this is what we call high mass stars. The intermediate stars from 2 or 3 solar masses up to 8, they have this dichotomy where they could end in a neutron star, or they could end in a black hole. But those ones bigger than 8 are almost always going to become a supernova. So what happens to them is generally you have the core, which is the part of the star, it's dead center, and it starts off just as a little nebular cloud, right? And that nebular cloud hopefully has enough matter around where it can start to gravitate towards each other, towards the pieces, so you get more and more piling up. And eventually it becomes opaque to infrared radiation. So it sort of acts like a blanket or a cocoon holding the heat in. And that allows it to get bigger and more massive and hotter. Well, once it reaches about 10 million Kelvin, then the average kinetic energy of the molecules, usually atoms, but sometimes molecules as well, will be large enough that you can force hydrogen to run into hydrogen. So hydrogen nucleus, which is basically a proton, running into a hydrogen nucleus, which again is a proton. That's 2 protons. They're like charges. They repel, and the nuclear force, the electric force is very, very strong. In fact, it's the second strongest force in nature. But luckily, if you can overcome that part by going so fast as you go if you're at 10 million Kelvin, then you can overcome that force and get close enough, about 10 to the negative 15th meters, where those protons are sucked into each other and become a proton. And actually, oddly enough, it spontaneously, one of the protons turns into a neutron and spits out a particle to conserve energy and to conserve mass and to conserve momentum. And you got a proton neutron there. Now that proton neutron might run into another proton neutron, and boom, they stick together, but it actually takes another step. And then boom, ultimately you get 2 protons, 2 neutrons, and that's the nucleus of a helium atom. Okay, so we've got basically hydrogen and helium from the get-go. All the other things, the lithium, beryllium, boron, they're all just trace elements. But hydrogen and helium are pretty prevalent. About 75% hydrogen, about 80% helium by the numbers, not by the mass. Excuse me, 75%, 25%. If you do by the mass, it's significantly more, because helium is so much heavier than hydrogen. But inside the star, you're taking hydrogen and turning it into helium. So you're getting more helium as days go by. And these reactions are literally billions upon billions. They're like 10 to the 38th every second, collisions like this, or I should say nuclear reactions like this, called fusion. So that is what actually creates the energy, because it turns out, if you sum up the mass of 4 protons, which is ultimately what it takes, and you compare that to the mass of the helium atom, nucleus that is, you find out that there's actually a decrease in mass. And that decrease in mass, if you multiply that by c squared in the famous E equals mc squared equation, you get the amount of energy that one of those fusion reaction gives off. If you then take the total amount of energy put out by the sun and divide it by that energy per collision or per fusion, then you will learn exactly how many fusion reactions must take place in the core every second. And we did that, and we made instruments to detect the particles coming off of it, specifically neutrinos. And we went underground over a mile, and we paid hundreds of thousands and millions of dollars, and we built an Olympic-sized swimming pool, only it was a detector for detecting neutrinos. And with all that work and all that time that we put into it, we predicted that we would get 3 neutrinos a day. Really kind of disappointing. They turned it on, first day they got 1. That was a little disappointing. Maybe we started late, right? They turned it on the second day, got 1 again. Second day, 1, or third day, 1 again. In fact, they were only getting about 1 per day on average. And they were like, oh, this stinks. We really thought we understood the sun. Well, some wiseacre says, hey, what if there's 3 types of neutrinos, and spontaneously the neutrino can change types on its way from here to from the sun to here? They're like, well, that seems really specific and made up, and back of the envelope bull crap right there. Well, guess what? They hypothesized it. They worked out what it would be, and in fact, that causes the neutrino to actually have some mass, not zero mass, even though it travels very close to the speed of light. And they figured out what the three neutrinos would be like. In fact, there's an electron neutrino, a tau neutrino, and a muon neutrino, and that they in fact do spontaneously turn into one another because they have mass and therefore can. And in fact, when they built the second detector that was capable, basically by using dry cleaning fluid, capable of detecting neutrinos and telling which type of what, they got exactly the right number. So they did understand what was going on in the sun. In fact, the reaction that Hans Bethe that I just told you about had told them about was exactly the reaction that does keep the star growing. Well, that reaction, those many reactions are shooting out radiation. That causes a radiation pressure that pushes out. All the mass on the star out here is squeezing in because of gravity, but it's got to constantly be in equilibrium or bad things happen. So it's just that interim part that's hot enough to really have fusion going on, but that's got to be big enough that it can produce enough radiation to keep gravity at bay. Well, eventually, since our models show us that stars don't circulate matter except when they're really, really small, really, really low mass stars like half of a solar mass and smaller, those stars actually have the ability to circulate matter from the outside into the core. All the other stars don't. Our models, which have many ways of testing, are not unlike global circulation models that we use for global warming, but they predict a lot of stuff, and it shows that they don't have circulation. And because they don't have circulation, pretty much only the hydrogen in that inner core is the only part you get to burn, right? So eventually you're going to start running out of hydrogen. When you start running out of hydrogen, and in fact, if you run out of hydrogen and the star is big enough, there's no real, loss of transmission or anything like that. In fact, it all happens sort of instantaneously. But if it's small, what will happen is you run out of helium in the core, and all of a sudden gravity will squish it, and it squishes down. Well, it got smaller, so it got hotter. So now there's enough area inside of what was outside of the core now is now inside the core because it shrunk. So you've got some new hydrogen that can actually be fusing, but just on the outside edges of what used to be the core. So that's what happens when it's a low mass star. And if you get it hot enough, then you might even be able to reach 100 million Kelvin. At 100 million Kelvin, you can start fusing helium into carbon. But with a big mass star, it just automatically jumps in and starts fusing hydrogen or helium into carbon. So it fuses hydrogen into helium, it runs out of hydrogen, and boom, instantly it's so massive, it squeezes it so tight that it reaches that 100 million Kelvin, no problem, and it starts fusing helium into carbon. Then it runs out of helium, it starts fusing, actually it's carbon and oxygen, some other stuff, and same thing happens now. Now you can start fusing carbon and oxygen and other stuff, and you end up getting a giant gobstopper, basically. So you end up getting a star that has in its innermost some thing burning, and in fact the dead end, the nuclear dead end, is fusing to create iron. So iron's the end of the road for fusion or fission, because it takes more energy in to fuse into hydrogen, and it takes more energy in to fizz out of hydrogen. So fusion and fission is breaking apart one big thing making two smaller things, and then fusion is two big things making a bigger thing, or two small things making a bigger thing. Neither one of those are energetically favored for iron. So iron's the dead end. So at the middle of that gobstopper is something fusing, making iron. And then outside of that is the previous element fusing. And then inside of that's the previous element. And then when you get to those last three layers, it's like carbon's fusing, and then hydrogen's fusing, or helium's fusing, and then hydrogen's fusing on the outermost shell of something like a core. And the rest of the hydrogen and helium of the star is just out here doing nothing. But once it reaches there, it can't fuse any farther. Once it runs out of whatever it's doing to fuse into iron, once it runs out of that fuel, the core will collapse. And in fact, it turns out that neutrinos play a major role in this. We don't exactly understand all the details, but it implodes, it crushes itself, and then sort of backlashes and explodes outward in what we call a supernova. And it's just called a supernova. It's not a nova, and it's not a type 1A supernova. This is just a supernova. And basically, that energy is so high that it burns more light than all the stars combined in our Milky Way galaxy. Okay, but it does it for on the order of a couple of weeks. I actually saw one 100 and I think it was 160 million light years away. I saw a single star in that galaxy was brighter than that whole galaxy, and I saw it through my telescope. Even though we were looking in the north where all the light pollution was from our telescope. So it was really impressive, but that's a supernova explosion. That supernova explosion has such high energy that all the elements that you skipped in getting up to getting up to iron, all of those elements can now be accounted for, except for the, maybe some of the ones that are short-lived, and even then are probably possible. So that actually explains how we get the rest of the periodic table, because it turns out as you're going up through those elements, you burn hydrogen to fuse into helium, you fuse helium into carbon, and actually you fuse in a couple other things too. And then you fuse carbon into something else, and then you fuse that into something else. They're going up sort of like by 2 elements each time in the periodic table. So there's a bunch of little slots on the periodic table that were missed. But when you calculate the energy of the supernova explosion, it turns out that energy makes it possible to create all the other elements. And in fact, you now know that the iron in your blood was once inside the core of a star that blew up in a supernova explosion. That's the only thing we can assess as creating the carbon, creating the iron that we have. That's also the only thing we can account for creating the gold and the silver and the platinum in our universe. And that's why those things are so expensive, because they're so rare, right? So that's the life of a of a large mass star, 8+ solar masses. That intermediate one, I told you, they can sort of go through the same process, but they never get to fusing into iron at the core. And in fact, they get so heavy that they sort of die out, and the gravity shrinks it so much that only neutron pressure. Remember how electrons there's only a certain number of electrons that can go in a level in an atom, according to the Bohr model. Well, quantum mechanics says that there's only a certain number of electrons that can be in any state. In fact, they all have to have different quantum numbers. Well, the same thing, only a different way, is true about neutrons. There's a maximum number of neutrons you can fit in a space or a state, or whatever you want to call it. And when gravity crushes it and doesn't go above some huge amount of force, it basically forces all the electrons of the atoms of the star into the nucleus, and spontaneously they combine with the protons to make neutrons, and you get basically a city-sized, or maybe in some cases as big as a state-sized star that's made essentially out of neutrons and held together with the same density as a nucleus. And that's what a neutron star is. If, however, the gravity is even bigger, in other words, the mass is even bigger than that, so it completely overcome that force of keeping neutrons apart. If that mass is big enough to overcome that, then it just becomes a black hole, shrinks to nothingness, and in fact has no ability for even light to leave it. There may be some light created at the outer surface called Hawking radiation, but there's certainly not going to have any light leaving it. And once you get to a certain distance, called the Schwarzschild radius, which is 2gm over c squared, once you get to that certain thickness or radius, you're sucked in, and there's nothing else you can do about getting out of it. And if the black hole is small enough, it's going to kill you anyways. It's going to stretch you and compress you, so you become like as wide as a straw but as long as a mile, right? So that's what the black hole is going to do. Now here's the weird part. The stars live on the gas that's in them. That's like their fuel tank. So it would seem, if I had a car with a 20-gallon fuel tank, I could go a pretty good distance, especially if it's good on gas. So I might reason to myself, well, let's put a 60-gallon gas tank on there. And let's say the 20-gallon gas tank got me 300 miles. So if I put a 60, I expect I'm going to get maybe 900 miles or 600 miles or something, right? Well, what would happen if you replace that 20-gallon gas tank with a 90-gallon gas tank and expected 900 miles, but instead got 280 miles? That's what happens with a high mass star. It turns out high mass stars, because they're so massive, they actually make the core temperature so high that there's another longer, crappier reaction process that goes on called the CNO cycle. It uses carbon, nitrogen, and oxygen, but it does the same thing as fusing hydrogen into helium, but it does it through these intermediates that you might have learned about in chemistry. Anybody learn about things that speed up reactions in chemistry? You remember what they were called?
Catalysts.
There you go. Yeah, I was going to do a meow if y'all couldn't think of it. So yeah, it's catalysts, and that's what these are. They're nuclear catalysts. The carbon, nitrogen, oxygen are nuclear catalysts. So the reaction is actually quite a few steps longer, but still it happens way faster. And because of that, they burn fuel super, super fast. And that's sort of what would happen. You know, if you had a little Prius and you put a 900-gallon fuel tank on it, the Prius would waste all its gas trying to go the first mile, or waste all its energy trying to go the first mile, just because it's so much heavier, right? And that's what happens with a high mass star. They live short lives, and the higher the mass, the shorter the life. So some of these high mass stars only live for like 1 million years. Well, that's a problem, because as best we can tell, we are all parts of a common ancestor. In other words, there's one ancestor in the past that's sort of granddaddy or grandma to all of us. And meaning you are cousins with an octopus, with flagellum, with COVID, with cucumbers, with trees, with grass, all that stuff. That's the fundamental idea behind biology nowadays, is the evolution of life. And all of the living species have overlaps in our DNA that happens to match exactly what biologists found before Darwin came along. Biologists would look and they'd find, you know, crests on a skull. And if the crest was like this, it would be part of this group. And these two had similar crests, so they probably were cousins in some way. And they were descended from this other ancestor that had a more pronounced version of one of those, that sort of thing, right? And lo and behold, when we got to studying DNA, it turned out all those, or essentially all of those predictions they made about things being connected to one another, were all right and supported by the DNA. So, for instance, if we had something that was very ape-like, say 5 million years ago, it might have had a child, and then it had another child with another ape-like dude, right? Well, one of these children had children, had children, had children, they had children, they had children, they had children, and ultimately we got to humans. And this other one over here had children, then they had children, then they had children, then they had children, and he came out with an orangutan. Well, it turns out the DNA similarity between an orangutan and us is something like 95 or 99%, I can't remember, but it's a huge overlap. That means that was fairly recent in the past. So we're not descended from apes, we're not descended from orangutans, but we have a common ancestor. That's the deal. Well, as you can tell, I said 1 million years ago. That's a pretty long amount of time, but guess what? That's like the length of a high mass star's life. So a high mass star is not going to live long enough for us to have evolution take place and create the advanced species you see before us. I mean, not us, I'm talking about whales and stuff, because clearly we ain't got our crap together yet, right? So guess what? It's again, like God left a little step stool to look over the edge inside the sink to see what's going on. We have this idea that we need a star that lives for a long time, because we need something to supply energy for cyanobacteria to evolve to something else, to evolve to something else, to evolve to a self-replicating molecule, to evolve to a self-replicating molecule with a nucleus, to evolve to a self-replicating molecule with a nucleus that then can make a more advanced species of multi-cell life. We need billions of years to do that. And it turns out only low mass stars do that. So our star, for instance, will live for about 10 billion years. And that's good enough, you know. And in fact, it looks like from our fossil record, about 1.5 billion years after our Earth came into solidity, in other words, it came from a horrible liquid with a horrible atmosphere, it actually became a solid and had a mostly carbon dioxide atmosphere. It turns out that was really good for cyanobacteria, but the cyanobacteria were taking it through photosynthesis and taking that CO2 and making it into oxygen. And then the oxygen became toxic to a lot of different things, but that allowed things to grow in other ways. And then some creatures left the earth, some creatures left the earth by other means. Some of them were not creatures at all, but more like grasses and stuff like that. And we slowly evolved to what we have now, to all those different species. So that's sort of the big picture of what's going on. Now, in order for us to make some sense of that, we still need to know some basics. So I've told you how the Big Bang predicts what's happening. You can look at that table or that little graph on page 1216 and see the timelines for that, so you can answer the questions. You'll see there's something called a scale factor that is basically the change in wavelength divided by the original wavelength. That's basically the Doppler shift that happens due to the universe expanding. Well, that turns out to be equal to 1 plus z, the scale factor. And the scale factor is what you multiply. Remember when I had that little wave multiplied by x, or saying the length from one peak to the other peak was x, and then I had to multiply it by something to make how big it is now? That z is the scale factor, not the z I drew, but the z in your book is the scale factor. So it's the z over the capital Z over the capital X that I put in there. So that's some stuff you need to do. You need to understand the sizes, and you need to understand, for instance, the measures of distance. And that's a few things I'm going to calculate for you really quickly with the 9 minutes we have left, because that's really the only stuff that's it's not even difficult. It's just a matter of having to do it. So one of the units of distance we use is the light year. And actually we use more than the light year, as you'll see in a second. So the light year is the distance light travels in 1 year. So distance is equal to velocity times time. So that's 299,792,458 meters per second exactly. In other words, that's the very definition of light year. In other words, we've defined the meter and the second in terms of this now. As I showed you, the calculation at the top of the other page gave us 3.155, I think I had 6.9 or something like that, 155,693 times 10 to the 14th. Again, you could just use, times 10 to the 7th. You could just use pi times 10 to the 7th if you want. And that's a nice little approximation. But when you do this, you actually get the distance in meters of a light year, and that distance is 9.46. And I can carry a couple extra digits, so I'll say 9.460528 times 10 to the 15th meters. Okay. For some perspective, remember the distance from the Earth to the sun was 1 astronomical unit. And 1 astronomical unit, if I remember correctly, was about 1.49 times 10 to the 11th meters. So this is on the order of 10,000 astronomical units, but that's a light year. And the nearest star to us other than our sun is Proxima Centauri. And it's actually a double star, by the way. Proxima Centauri, which is about 4.2 light years away. Okay, so that is 1 light year, and it's equal to that 9.46 times 10 to the 15th. Now, it turns out, for instance, the distance from our moon to us, so Earth-Moon distance, that's equal to 1.28 light seconds, okay? In other words, it takes light reflecting off of the moon about 1.28 seconds to get to the surface of the Earth. And you might recall that from Big Bang Theory when Penny had started dating the appetizer dude. They took him up on the roof and they shot a laser at the moon. We happen to have left mirrors on the surface of the moon for just such experiments, and you could detect how long it took the laser to shoot and how long it took to turn back, and you could exactly calculate the distance between the Earth and the moon. And that's a really good thing we can do for planet to moon or planet to planet distances, but that's pretty much all the range we can do on that. You could also find the distance between the Earth and the sun, and that turns out to be about 8.3 light minutes. So if the sun went out right now, the center of it would become black but that's on about 8.3 minute delay. So we wouldn't know it for 8.3 minutes. The whole thing, even if it went black at once, to us, the center, since it's the closest part, would go black first, and then it would spread out blacker and blacker and blacker until the whole face went black. But it would be on an 8.3 second time delay. Pluto, on the other hand, from the sun to Pluto is on the order of several hours, like 4.5 hours or something like that. So that gives you some ideas of times. Well, there's also another unit of time or units of distance. I keep saying time. Sorry about that. There's also another unit of distance that's very common, and I've already talked about it. It's the parsec. And what you do is you do surveying techniques. So you imagine, for instance, the sun right here. You can say the Earth is right here, and that would be in July. And then the Earth is going to be over here in January. Okay. And you see this distant star right here compared to all the background stars. And what you'd see is from this area, the star looks like it's that way, meaning it's in that direction. And from this area, the star looks like it's that area. And in fact, or in that direction. And in fact, this angle right here, theta, is called the parallax angle. Basically, if you took a photograph of it in July and you took a photograph of it in January, it would appear that this star has moved over some distance. You know, the photograph that you took based on the telescope that you use has a width, say, of 10 arc minutes. And if you saw that the star moves, say, from here to here, you could, and say this is, let's say 8 arc minutes. You could then tell how many arc minutes it moved, and that would be twice this angle, right? So that's what that star would do in going from July to January or January to July. And half of that angle is the parallax angle. Okay. Now, it turns out if you measure that in arc seconds, which is really the measure that you have to do, because an arc second, 1 arc second is equal to 1 over 3,600 degrees. So you know how small a degree is. Now imagine dividing that up by 3,600. That's what an arc second is. If you do that, then it turns out the distance the star is away in parsecs is equal to 1 over the parallax angle in arc seconds. Or the parallax angle in arc seconds is equal to 1 over the distance in parsecs. So that's the method they use. And it turns out that this distance right here, if this angle is 1 arc second, this distance would be 1 parsec. So theta equals 1 arc second. Notice a single one's an arc minute, a double one's an arc second. Then this is equal to 1 parsec. And like I said, 1 parsec turns out to be about 3.26 light years. So it's bigger than a light year by about a factor of 3.25. So that's another measure, another way we can measure the distance of stars. But it turns out, like I said, the distance of these things is the hardest part. But I already told you about Henrietta Swan Leavitt and her Cepheid variables. Cepheid, because it's from the constellation Cepheus, there's a star in there, and you can still look at it to this day. Cepheus looks like a house, but one of the corners is sort of jacked up. There's a star here, a star here, a star here. At this corner down here is jacked up, but it also has an extra star there, and it's got a star there in the middle. And you'll see that near the Little Dipper, in fact. And I think it's this star right about here is the Cepheid variable. And you can watch it and, like, say, compare it to a star whose brightness, you know, maybe this is a magnitude 1 star. You say, okay, on December 8th, this was a 1 magnitude. You go back and look, and now it looks like it's as bright as that star. Maybe that's a magnitude 3 star. So you now say, December 18th, it was a magnitude 3 star, so on and so forth. And you can actually get a plot of it and use that just like Hubble did. So that's one way to measure distances, and that gets us a long way. As long as we can see a Cepheid variable and get it to enough resolution that we can make out how its brightness curve changes, anything that Cepheid variable is in, whether it be a cluster, a nebula, or a galaxy, we can use that to measure distance. Then we can also use certain things like type 1a supernova. I already talked about supernovas, but this is a type 1a supernova. And that's a supernova that basically is a white dwarf. So when our sun runs out of hydrogen in its core, it's probably going to be warm enough to fuse a little helium into carbon, but not much. And it's never really going to explode in a huge way. But eventually what's going to happen is it's going to start fusing in here in the core. It'll expand, it'll become a red giant. Some of the matter will be lost, and in fact, it will absorb part of the, it'll absorb Mercury and Venus and maybe even the Earth, and it'll be a red giant. And then all that stuff will sort of be blown off, and then it'll shrink back to a white dwarf, which is basically a pile of carbon atoms that's super, super hot, but maybe the size of Washington, D.C. So that's a white dwarf. Well, if that's near to another star, then it can actually suck matter onto it. And once it reaches a critical mass called the Chandrasekhar limit, it will actually go into a supernova. And we know exactly how luminous that is. So if we happen to see a supernova of type 1a in another thing, then we can measure that because it's going to be as bright as a supernova. So that can get us, megaparsecs away. We can also do other things, but that's basically it. That's the science of astronomy. We can tell what's in the elements, or excuse me, what's in the stars by looking at the spectra. We talked about the Bohr model of the atom and that having very distinct wavelengths or energies associated with the energy levels. So these are gas tubes that basically have different elements in it. If I shot this light through a slit and then sent that light through a spectrum, through a prism, you'd get little indistinct lines, or very narrow lines anyways, of very distinct colors. And that would, for instance, look like these guys. Actually, no, this is the absorption spectra. This is the one that I was going to say there. So you would get something like these guys. This is the one for hydrogen. Okay. This is some others. This is called an emission spectra, and this is what nebulas give you. And each of those colors are represented by a distinct transition. And if it's moving towards us, we have to correct for the Doppler effect. But once we correct for that, then we can say, oh, well, this is the element hydrogen. And you see others say, oh, well, this is the element oxygen, or diatomic oxygen, or this is nitrogen, or this is water. That's how we can tell what's in a nebula. If we look at a star, it's going to have a hot, dense core that would produce a whole rainbow like this because of its high density. But if that hot, dense core is covered by a loose, cooler atmosphere, like a star is, then you get what's called an absorption spectra, which is a rainbow missing colors. Notice these missing colors are exactly the ones that are existent here. So this is the spectra of the same thing. So by using those spectra, we can not only tell what elements are present, but we can tell in what quantities, and we can tell how fast they're rotating, or we can tell how fast they're moving towards us by their Doppler shifts. So that's the big picture of astronomy. That's how we know the things that we know about the universe. It's not that we're making stuff up, but it's pretty amazing. Stars live on average, the high mass stars live on average millions of years. The low mass stars live tens of billions of years. We've only had a telescope for about 250 years or something like that, or excuse me, 450 years, and still we managed to put together the life cycle of a star. So it's a really amazing thing that Americans have done, and that's a total counterpoint to the Copernican revolution, which said we're nothing special. So anyways, you guys are free to go, and that's our last lecture. I've enjoyed having you. You do not have to meet for class any next week, but you do have a final on Monday that can be started as early as 4:45. But you're allowed 2 hours and 15 minutes, I think. But if you start later than 5:45, you won't be allowed that time. You're going to cut yourself short. Every minute you start after 5:45 is going to cut out a minute of how long you can take it. So make sure you start on time, and contact me immediately if you have something that's preventing you from doing it on that day, because if you don't get it done today or tomorrow, I'm probably not going to be able to help you. So I did set it up for someone to take it at a testing center, and I set it up for another person to take it the day after what I've made them a new exam. So I'll wait around for the last of you in case anybody has questions. I hope you all enjoyed that discussion. Gavin or Nate, you have any questions? Awesome. See you guys. Have a good one.